Okay. Good afternoon, everyone. Welcome to your latest IRIS webinar. This is your host, Danielle Sumi, and I'm speaking from the Incorporated Research Institutions for Seismology, headquarters in Washington, D.C. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. Today's research-focused webinar was solicited to highlight important scientific results and, in particular, is part of a series highlighting professional development and education topics to lower energy and knowledge barriers associated with careers in science. And Fred has given a webinar before on careers in the petroleum industry. Those who are interested in additional resources aimed at early careers can check out our website, which is off of the main IRIS website and just /ECI. In addition, webinars are recorded and archived on the IRIS YouTube channel. The webinar ground rules are only the presenter, in this case Fred Schroeder, and I will speak. If you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the box on the webinar control panel. At the end, I will read your name and question to the speaker. If similar questions have been asked, I may combine or simply skip them. If the webinar crashes, which has actually happened once, I will reboot it. Just click the email, the link that you received via email when registering. And at the end of this webinar, I will be sending out a short 5-minute survey via email. Your opinions and insights will help us inform future webinars. One of the questions we'll ask if you're watching this remotely in groups. So if it's more than just you in the room, please let me know. I also wanted to let this audience know that the deadline to apply to attend the NSF-sponsored Subduction Zone Observatory Science Workshop is next Wednesday, June 1st. The workshop will be held in Boise, Idaho from September 29th until October 1st. It seeks a broad range of applicants interested in discussing the scientific motivation for an interdisciplinary Earth, ocean, and atmospheric research program focused around the scientific questions and societal hazards related to subduction zones. There's also limited travel support available for the workshop. And so you can visit our website at www.iris.edu for more information. Today's webinar is part of IRIS's continued efforts to engage students, postdocs, and young faculty with resources to enable their professional development. And our presenter is Dr. Fred Schroeder, who has 39 years of experience in oil and gas exploration, research, and training. After earning his PhD in marine geology from Columbia University, he started a 32-year career with Exxon and ExxonMobil. His main skill is seismic interpretation, with an emphasis on seismic stratigraphy and seismic attribute analysis. Fred taught many in-house schools for ExxonMobil and Noble Energy and has taught a graduate course at Texas A&M. And in addition, has participated in over 75 short courses on university campuses across the United States. Thus, without further ado, here's Fred to talk about hydrocarbon play elements from a geophysical point of view. Thanks, Fred.
Thank you, Danielle, and good afternoon to everyone. If you tried to see this webinar a month ago, my apologies. We had a severe weather system go through the day before, and we were without power for 28 hours. And that was kind of a showstopper for our seminar that was scheduled last month. So today I'll talk about hydrocarbon play elements, and it will be from a geophysical point of view. And my slide, oh, there. So I'll give a quick outline. First, we'll have to talk about what hydrocarbon play elements are, in case you're not aware of them. We'll talk about the data that is used to evaluate plays. We'll talk about the importance of reflection seismology. I'll walk you through a basic workflow, talk about how we develop a geological framework, and then how we build a series of play adequacy maps. So we'll talk about play elements. Rube Goldberg was an illustrationist who had a niche, and what he did is he made very complicated devices that would do a very simple task. And if you ever played the board game Mousetrap, that would be a Rube Goldbergian type of device. So if Rube were still alive and I could ask him about a hydrocarbon system, he would say, well, Fred, it's pretty simple. First, you need a kitchen, a place where organic material is cooked. And then you need a container where we can produce or get out of the ground oil and gas. And since the kitchen and container are usually in different rocks at different levels, we need some plumbing to connect the kitchen to the container. And then, of course, we have to put the well in the right location, so we hit the container. And if we get all of that right, then the oil comes out of the ground and money goes into the bank. Well, that's not really a Rube Goldbergian illustration, because it's taking something that's very complicated and simplifying it quite a bit. Being a little bit more technical, what we would need is a source rock that's going to generate our oil and gas molecules. We need hydrocarbon migration to get those molecules out of the source interval and into a reservoir. And the container has three components. We need a reservoir quality rock, we need some sort of three-dimensional trapping geometry, and we need a seal to hold the hydrocarbons within the reservoir in the trap. This is for conventional types of exploration plays, not the unconventional or resource plays that have been hot topics for the last 8 or so years. Looking at a little bit more detail for our source, we need organic rich rocks, usually shales. The best sources are shales that were deposited in a low oxygen or I've lost that word. We also need temperature and pressure conditions that result in the transformation of raw organic material into oil and gas. For the container, we need a reservoir, a rock that is porous and permeable so that we can get fluids out of it. The most common reservoirs are sandstones or certain types of carbonates that have good porosity and permeability. The trap, we need a three-dimensional configuration in the subsurface that will pool or collect the oil and gas. We need to get a large enough quantity of oil and gas so that it will be economic to go after. Those traps could be purely structural, like an anticline. They could be purely stratigraphic, like some sort of a reservoir sand pinch-out, or it could be a combination trap where part of the trapping mechanism is related to structural elements and part of it is due to stratigraphic elements. For the CO, we need a rock that prevents the leakage of the hydrocarbons out of the trap. The most common seals are shales and any type of evaporite or salt deposit. We need seals on top of the trap, and we also need lateral seals so that we get a thick enough oil column or gas column so that it will be an economic discovery. For hydrocarbon migration, we need to get the generated oil and gas from the source into the porous reservoir. And again, that is for conventional fields and plays. Some of that hydrocarbon migration may occur parallel to strata, making use of sand and silt layers. Some of that migration may cut across stratal units, going up fault zones or through fracture networks. In evaluating an area, we will have a certain amount of geological data. We may have some nearby wells, and those wells may have core, or they may have sidewall cores. We would probably have a series of well logs that were run through the well bore to get different measurements of rock properties and fluid properties. There may be outcrops that are adjacent to the area we're studying where we can see age equivalent formations and analyze and study those. Or we may have a situation in the subsurface that is analogous to something that we have outcrops for somewhere else in the world. In terms of geophysical data, we have reflection seismic data. That could be a 2D seismic survey or 3D seismic survey. We may have gravity data that gives us information about the local density structure of our study area. We may have magnetic data that will help us understand the magnetic structure. And we may have electromagnetic data that can help us to determine if hydrocarbons are going to be present in our study area. Reflection seismology is very important, especially in exploration. If we're talking about an exploration project, what we want to do is identify and lease areas that we think have the highest potential for oil and gas. And once we have some areas that have been leased, we want to drill wells and to find the hydrocarbons, the oil and the gas. If we are working in exploration, you may not have any local wells. And the nearest well to your study area might be 50 to 100 to many more kilometers away. We need to make pre-drill predictions as to what we anticipate we will encounter in terms of the formations and the temperatures and the pressures and the presence of oil and the presence of gas. So how can we know the local geology? We have to rely quite heavily on geophysical data. And reflection seismology is the tool that is used most significantly in terms of trying to get a picture of the subsurface and make pre-drill predictions. So I'll walk through a basic workflow. The first thing we have to do is acquire and then process the seismic data. Then we do our seismic interpretation. We may have adjacent wells that we can tie to our seismic. We'll have local seismic data that we can analyze. That could be 2D or 3D. And if we have adjacent wells, we can go through a step called well seismic ties, and I'll show an example in a minute or two of what that is all about. Once we have our interpretation started, what we are trying to do is build a geological framework. Talk more about that in a few minutes. We then want to identify prospects, places where we think we might have significant oil and gas that we can tap into and produce. We have to evaluate those prospects as to what we think we'll have and how confident or certain we are that hydrocarbons will be found there. And then we have to make business decisions. Depending on where we are in an exploration cycle, we may be trying to get new acreage, and so we may be bidding on some blocks that are up for sale, for lease, or we may have some lease blocks and we're trying to decide where to drill our first exploration well. So we have to acquire our seismic data. This is a picture of some land vibrators that are our sources. We have to do a lot of seismic data processing to get images that someone like myself, a seismic interpreter, can use. And then we will go through a series of interpretation steps to try to understand the structure, the stratigraphy, the lithology, rock properties, fluid properties, and where oil and gas may be reservoired in a quantity that would be economic. So looking at the interpretation process itself, we'll have our local seismic data. That could be a 2D grid of data. It could be a 3D seismic survey, or it could be a combination of 2D seismic and 3D seismic. If we have wells in our study area or adjacent to our study area, what we can do is generate a synthetic or a modeled seismic trace, tie that to the real seismic data, and then relate the information that we have from our wells, either through cores or logs, to the wiggles that we have on our seismic data. So this is an example. This is onshore Texas data, fairly old data, but you can see the black and white wiggles in the background. There's a red, a green, an orange, and a blue horizon that has been mapped. Those are formation tops. And then the red squiggly line in the center is a model trace based on well information. We use the velocity log and the density log to calculate reflection coefficients, convolve that with a seismic pulse, and we generate an idealized seismic response. And this allows us to take information such as the depth to the top of the Austin Chalk and relate that to a particular part of our seismic wiggles, a peak or a trough or a zero crossing. We'll use our seismic interpretation tools to try to build a geological framework. And by that, I mean we're going to use all the available data, well data, seismic data, outcrop data, regional studies, gravity, magnetic, anything else that we can get our hand on to try to get the present-day framework of the structure and the stratigraphy. We'll do a structural interpretation, trying to map out faults and folds, try to understand areas of subsidence and uplift, figure out what sort of structural trends we have and what sort of structural features like a series of anticlines that might form traps. We'll also do a stratigraphic interpretation, looking for stratigraphic unconformities, different types of stratal packages or depositional sequences, try to determine the depositional environments, and from that figure out what sorts of lithologies we have, and we may have to use seismic interpretation to try to figure out the ages for the different horizons that we map. On the right is a little diagram showing 1, 2, 3 horizons intersected by 1, 2, 3, 4, 5 different fault planes. And so the geological framework is the series of faults and major horizons that will be the skeleton that we'll then use to analyze individual intervals of interest. We want to identify prospects once we have our framework built. And a lead is something that is an interesting feature. It could be some sort of an anomaly that we see in the data. It might be a structural anomaly like an anticline. It might be an amplitude anomaly, such as a real strong negative or positive set of reflections. And a lead is something that has the potential to be an economic discovery. What we'll do is we'll identify the leads and do more work on it so that we mature the lead into a prospect. And my definition of prospect is something that I would be ready to present to management as a possible drilling location. So here's an example. This is an example from the Gulf of Mexico. What we're looking at here is a map showing seismic amplitudes. The reds are very negative numbers. The yellows and light greens are close to 0, and the blues are positive numbers. And you can see this anomaly in red that's indicating extremely low reflection or seismic reflection values, large negatives. And in this particular area, large negative seismic amplitudes is usually a flag or an indication that we have a gas sand. In this case, we have a fluvial system, a fluvial sand, and here's the main channel. And this is interpreted to be a splay off that fluvial channel. And so we can use this seismic amplitude attribute map to outline what we think would be the extent of the gas. I called this the Tiger Prospect. They're Miocene age fluvial sands. The source rock is deeper in the Oligocene. We have a marine shale that caps the fluvial sands, and that forms mycel. We have a three-way closure on a fault. So we have a high point west to east here, east to west here, and northeast to southwest here. We anticipate, based on our analysis, this will have 50 billion cubic feet of gas, and we've determined that there's a 78% chance that if we drill this, we actually will have enough gas that it would be economic. So these are the types of things that management would want to hear. What kind of play do you have? What's the type of reservoir? What type of source? What type of seal? What sort of volumes are you talking about? Is it oil? Is it going to be gas? How much oil? How much gas? What's the quantity? And then how certain are you, or what's the chance of success? Once we identify a prospect such as the Tiger Prospect on the previous slide, the next step is to evaluate the prospects. In terms of the source, we need to have organic material. That's plant remains or animal remains. We need reaction conditions. We need a certain amount of time and burial and temperature. And if we have the organic material and we have the proper burial, temperature, pressure conditions, we'll generate molecules of oil and molecules of gas. If we have a well in the area, we can get the present-day stratigraphy. And one of the ways in which we will analyze this area, we will backstrip this stratigraphy from present day back through geological times. So in this case, the well at its total depth is into early Jurassic, and so we've modeled how this particular location where the well is drilled has subsided and then received sediments. If we understand that the early Jurassic to the early part of the middle Jurassic is our source interval, if we understand something about the thermal history in the area, our geochemical friends have algorithms that they can use to model when the source entered into the oil generation window and when it passed into the gas-only generation window. And so this is a way in which we can look at some of the qualities of the source and how much oil and how much gas we think has been generated in the area that we're studying. We can look at the stratigraphy on our seismic. We can interpret the main depositional sequences, try to understand the environments of deposition, and then interpret what sorts of lithologies we would have. So in this case, the brown would be mostly fluvial sands. The yellow would be shore face or near shore sands. The light green is offshore silts and shales, and the gray would be basinal shales. We can do this for a series of 2D lines or for a 3D volume of data and come up with a map that shows the main depositional environments, non-marine or fluvial, coastal plain, shore face, slope, and basin. And this is a way in which we can then try to predict where we would have good source rock facies and also where we would have good reservoir rock facies. For trap and seal, we need a three-dimensional configuration in the subsurface. I showed you the Tiger prospect before. We have a fault here, high side on the northeast, low side on the southwest. We have a little bit of a high where the high negative amplitudes are located. Here's where the fault is. This is our reservoir zone. We can see very high amplitudes in this portion. It becomes moderate amplitudes over here. And so the extent of our gas we would predict would be about this far, where we have the strong white and strong black. We have an overlying marine shale that would form our seal. And we could make a prediction for this, the fluvial sand. The red would indicate where we would think there would be gas. Blue is where we would think there would be brine or water. And we even have where we think the gas to water contact would be on this particular seismic line. For hydrocarbon migration, each trap that we identify would have a certain drainage area. Oil and gas that's generated within a particular drainage area will percolate up and then move up dip to the culmination or the high point of the trap. So this is a map view. Below is an attempt to look at it in 3D. So we have a high point here. The blue would be synclinal axes that would separate one drainage area from another. So any oil or gas generated in this zone would migrate up dip and start to fill this trap. There's another anticline here. The blue shows a polygon that would be its drainage area, and so oil and gas generated within this blue polygon would migrate up dip into this trap. So this is an example from the North Sea. We have an anticline here. I'll talk about the name of it in a minute. For me, red means that it's a free gas cap. The green is an oil leg, and the blue rectangular polygon is the drainage divide for this particular anticline. So all the oil and gas that's generated within the blue polygon would percolate up, get into the reservoir quality sands, or sands, I should say, get into the anticline where hopefully it would be reservoir quality. So that's one local drainage area. This is the same drainage area as on the left, but now I've added another drainage area to the east, another to the southeast, and another one further to the southeast. This anticline is shallower. This anticline is the deepest. This one is the shallowest. These two are intermediate in depth. We filled up in this drainage area this trap until we have oil that's touching the drainage divide. If we keep adding hydrocarbons here, oil will spill from this drainage area into this drainage area and start to fill this trap. The oil again has touched a drainage boundary here, a drainage divide, and so if we continue to add hydrocarbon here, oil will spill and start to fill this trap. So we can model through time how oil and gas is generated, how it migrates through the subsurface, how it starts to fill traps, and if we have more hydrocarbon available to a trap than it can hold, we can also model the spillage out of one drainage area into another. So this is the area we were looking at in the previous slide. This deepest trap is the Huldra field. It has spilled oil and a little bit of gas to Oseberg. The Oseberg field is filled to spill, and it has spilled oil to the Braga field. And so this chart on the right is geological time from present back to 100 million years ago, and this is volume of oil. If we look at Huldra as an example, it started to fill with oil, and then the oil volume has decreased. That decrease in volume is because we put in so much gas that the gas has flushed some of the oil out, and that spilled oil has gone to Oseberg. Oseberg has filled with oil continuously, increasing in its volume through time, and then the shallowest trap in this case is the Braga field. It had no oil until about 22 million years ago, and then it started to fill with oil, and that oil is being generated in the North Viking Graben, and it has spilled from Huldra to Oseberg and eventually into Braga. We have to extract all this geology and all this information about hydrocarbons and where the oil is and where the gas is from our seismic data. So the interpretation of seismic reflection data is a very important process in the exploration game. We need to get great seismic acquisition in the field. We need the best possible imaging of the subsurface so that we can make our predictions. Our interpreters need to know how to extract geological details from the seismic data sets that they have to work. And so this is truly an integrated effort of geoscientists with many skills to try to understand the subsurface and make predictions as to where oil and gas might be and where we should spend money to drill exploration wells. So we've talked about the workflow down to business decisions. We'll talk about two different types of business decisions. The first is where we're early in an exploration cycle. There is some acreage up for sale, and we need to decide if we want to bid on some of the acreage that's available. The second business decision that I'll talk about briefly is drilling an exploration well on a block that we have already leased. So the first business objective would be to try to capture some opportunities to find oil and gas. So typically a company will do regional studies. The color-coded polygons here are examples of regional studies that a company may have done: North Slope of Alaska, Gulf of Mexico, Caribbean, West Africa, etc., etc., etc. They may find an area where it looks very promising for oil and gas. If in this area some blocks come up for bid or for lease from the government, then we would be interested in trying to decide if any of these blocks are promising enough that we should offer a bid, and we also have to decide how much money to bid. So in this case, a country has offered up 8 blocks. We have found leads in Block 7 and Block 8. We're going to do some more analysis to try to understand how much oil or gas there might be, and so whether or not we're interested in Block 7 or Block 8 or both. In order to do that, we'll look at different play elements, such as reservoir adequacy. The green would be favorable, kind of like a stoplight. Yellow is caution, and red is don't go there. So in this hypothetical example, our company decides that we'll bid on Block 7 and Block 8. In order to come up with that analysis or recommendation for management, we'll make a series of maps, one map for each of the main play elements. I show 5 play element maps here. One, where has the source been generating? Oil generation is in the green. Gas only is in the red, and then the white area on this map is where oil has not yet started to be generated because it hasn't had enough time, temperature, burial pressure for the organic material to be transformed into oil and gas. We have a reservoir facies maps here, fluvial to shore, shallow marine shoreline type of deposits. The blue would be a continental slope. The green would be an abyssal basin, and the gold color are deep water fans that have reservoir potential. The lower left is the structural traps. So the polygons in blue would be where we have anticlines and closure. The seal quality is shown in the lower center, poor to fair to good to excellent seal quality. And then the lower right is migration pathways. So we'll generate about 7 or 8 or 9 different maps like this. We'll look at where all the maps seem to have favorable indications that we have the elements that we need. And so we'll make a play adequacy map that shows where we have source, reservoir, trap, seal, and migration all looking favorable. So Block 7 and 8 in this hypothetical example looks good, and this area that's between 1, 2, 5, and 6 also seems to have a good alignment of the different play elements. If we have a block and we want to drill a well in order to find hydrocarbons, we may need to reacquire new seismic data. We'll process that data. We'll interpret that data. We'll refine our geological framework. We may find an interval where we think we have a possibility for reservoir quality sands. So we'll do an interval analysis. Here's a piece of a cross-section through a deep water channel system. This is a map showing a seismic attribute, and you can see the sinuous pattern for this deep water channel system. We've identified 4 leads, lead A, B, C, and D. The chance for hydrocarbon, A has a good chance for it, but it doesn't have enough volume that it would be economic, and so we're not interested in lead A. Lead B doesn't have a good chance for hydrocarbon. Perhaps there's no seal, or perhaps there's no mature source, or perhaps there's no reservoir. Lead C, we've determined we have a chance for hydrocarbon. It's big enough that it would be economic. We've considered how risky or what the chance of success is. It's past that hurdle, and so we would propose to management that we would drill lead C. Lead D also we think has a chance for hydrocarbon. It has a big enough volume, but it's got a lot of risk or a low chance of success, and so we have killed off that lead as well. We'll look at lead C, and we'll consider different possibilities. What if it's a fluvial sand? What if the seal is adequate? What if it's a tremendous seal? And so we'll come up with different scenarios as to what the hydrocarbon volume might be. This is hydrocarbon volume, million oil equivalent barrels. We decide lead C is most favorable. This is a map showing lead C. There's a salt diapir located here. We have an anticline. We think it has gas at the crest. It has an oil leg, and down dip from the green would be water wet. We propose to drill Wildcat in this location. We sell that to management, and an important part of being an explorationist is being a good salesperson. Our company drills the well, makes a significant oil discovery, and then we can start to do the next stage of trying to decide, is this something that we want to develop and produce? So there's various roles that seismologists play in this exploration process. We have to design the survey, and survey design, we have to worry about survey costs, which is increasing left to right, and the data quality that the survey would result, lower quality for lower cost surveys, higher quality for higher cost surveys. And so we get this red trace. And so if we spend a whole lot of money, we can get excellent data quality, but maybe we don't want to spend that much money. What's the minimum amount that we should spend to get the data quality that we need in order to answer the business questions? Then we have to acquire the seismic data. Previously, I showed you some land vibrators. Here we have a marine acquisition vessel acquiring data. It has the source array right behind the boat, and then the white further behind the boat are where the receivers or the streamers or the cables, the listening devices, are located. We then have to process the seismic. The processed seismic goes to someone like me, a seismic interpreter. I'll generate a synthetic well tie, and I'll make a well to seismic tie so I can get information from the well in terms of formations and ages and lithologies and relate that to the seismic wiggles. I'll do my structural interpretation. A series of fault planes are shown on the top center. I'll interpret a number of sequence boundaries or horizons. I have to worry about how horizons and faults intersect. I'll do my interval analysis, such as looking at environments of deposition and predicting lithologies, and then finding where I might have potential source rock, potential reservoir rock, potential seal rock. And then maybe I'll be able to identify a lead or a prospect and do an analysis. In this case, there's a seismic evidence for a fluid contact going from a gas-filled sand to a brine-filled sand. So this is a list. I won't be able to go through all of these, but these are the top 10 things that a geophysical analyst would work on. Detailed well seismic ties. We have various borehole geophysics that we can run to try to get information. We can model the area that we're looking at both structurally and stratigraphically. We can do quantitative seismic attribute analysis. We can do detailed velocity analysis. We can try to predict pore pressure before we drill the well. This is important so that we don't have a blowout. We have to convert our seismic from units of two-way travel time to depth in feet or meters, and we'll need our velocity information and our horizons in two-way travel time in order to do that depth conversion. We may have direct hydrocarbon indicators, DHIs. We may have amplitude versus offset anomalies, all of which helps us to verify if hydrocarbons are present where we are proposing that they are. And number 10, last on the list but not least important, we can do a process called seismic inversion to try to go from seismic wiggles to the velocities and densities and rock properties and fluid properties that we're interested in. So to summarize, geophysics is very key to our success in oil and gas, especially in exploration. We may have surrounding outcrop data that we want to use. We may have adjacent well logs. We'll have seismic data, perhaps only 2D, perhaps 2D and 3D. We may have gravity data. We may have magnetic data. We have a large toolbox of geophysical analysis tools and techniques. We'll develop a geological understanding for the area that we're interested in. We'll look for the different play elements, source, reservoir, trap, seal, migration. We'll look for where all of those are combining in a favorable fashion. We'll present prospects to our management, and then we can help management make the right decisions about what areas to lease if there's a lease sale going on, or where in blocks that we already have leases for should we drill an exploration well to try to discover oil or gas. So that's the end of my prepared remarks. I'll open it up for questions.
Great, thank you so much, Fred. We do have an initial question from Zigong Peng, who asked, can we drill through a salt dome?
We can drill through salt domes, and that's a very important in the deepwater Gulf of Mexico. Almost all the wells are drilling through thousands of feet of salt and then getting back into sedimentary section where they find quite a lot of reservoir hydrocarbons. And so beneath salt is a very challenging seismic imaging arena, and it does take a lot of seismic data processing in order to get the images so that we can understand the geology and locate the wells in the right location. Very good question. Thank you.
Sounds good. Well, that's the only question we have so far. So I guess with that, it's a small group today. Starting
okay.
Summer. But yeah, well, thank you, Fred. I appreciate it. And oh, we have another question. Thanks, Zigong. Zigong asks, how important is automation of salt dome and faults? Thanks, Zigong.
Automation of salt domes.
Did it autocorrect or something?
It's important for us to understand the evolution of salt features, yeah. Whether they're salt pillows or anticlines or overhangs. And if we get the present-day stratigraphy, including the salt and all the faults worked out, there are several different types of software packages that would help us to try to back out the history so that we could look at how the salt feature developed, the timing of it, and then relate that to when oil and gas was being generated and migrated. And one of the questions we always have to ask ourselves is a potential trap in existence when the hydrocarbons were percolating through the system, or did the trap form after the hydrocarbons were available? And so it's kind of like closing the barn door after the horses run away.
Mm-hmm. Okay. Yeah, and just to clarify, he did say delineation, so that was...
Oh, yeah. Yeah, it's very important to delineate the salt, and understanding where the salt-sediment interface is very important. And again, that requires very advanced seismic data processing to get the best possible answer.
Okay, great. Paul Freiberg wrote in, since we have a lot of time, can you say a little bit more about how velocity control is obtained? What is most commonly done in industry? VSP, sonic logs, or just mapping lithologies?
Well, the best velocity data comes from a VSP, a vertical seismic profile. For that, we need a well, and they have to tie up the well for maybe a day or two in order to get the data. And if you're talking, as an example, offshore Gulf of Mexico, at least until the recent crisis, the rate to have a rig out there was about $1 million a day. So VSPs are wonderful for geophysicists, but they're very costly. So we don't always have them. What we do have when we're processing our seismic data, we have to go through a process called normal move-out correction to try to flatten hyperbolic reflections. And when we do that, we do get an estimate of velocity as a function of depth. And so that normal move-out velocity, also called a stacking velocity, is what is commonly used. There's the first pass processing stacking velocities, and those are usually okay. If we have a prospect and it's important for us to have the best time to depth conversion, then oftentimes they'll go back. The interpreter has picked out where some of the main stratigraphic boundaries are. They'll do a velocity analysis that is keyed into the intervals defined by the mapped horizons, and that is usually a much better velocity analysis method.
Nate Kessler asks, is this type of work typically done in-house, or are you hired on as a consultant, or do you hire people on as a consultant?
Most companies do a lot of the work in-house. Seismic data processing often is contracted out to companies that specialize in that. And then there are companies that will do interpretation for under contract for a company. There are individuals that do different types of analysis on a contract basis. So it kind of runs the whole gamut. When I worked at ExxonMobil, I did a lot of the interpretation and modeling steps. I did a little bit of a project in seismic acquisition and processing, but that's certainly not my strong suit. So it depends on how big the company is, how much work they have, how much they want to do it in-house versus have it done by either a contract company or a contract individual.
Thank you, Fred. Benjamin Madara asks, in the conversion of time to depth seismic data, how can a
Yes.
model best account for thin beds, particularly those below seismic resolution as seen in some fluvial deposits?
Yeah, resolution is a problem both in terms of seismic interpretation and velocity interpretation. And usually what we do is we try to break the section into as fine detail as we can, and then do interval velocity analyses. If we make it really fine, then we'll end up with too many artifacts, and our velocities will probably be worse than if we used slightly thicker intervals. Again, it depends on how important the velocity time to depth conversion needs to be. If you're in exploration, usually you can live with 5% error in the depth. If you're working production, the depth conversion may need to be much finer, and then you may have to spend more money to get a good velocity model.
Okay. Zagong Peng also asks if you could comment on the price of acquisition.
The price of acquisition. I don't really have a good number in mind. I know with the downturn in the oil and gas industry, companies are getting real bargains in terms of acquisition and also processing because the companies that specialize in that are not very busy and they want to keep their people employed. But I know that for a survey that might take 6 months to acquire, you're talking maybe $10 to $50 million in acquisition costs.
Wow. Okay. Well, a lot more.
Do you want to mention the the chat that we are thinking about doing in the latter part of June?
Yeah, we certainly can. I was going to mention that, and oh wait, we have one more question. Gong is just like has so many. question. So let me do that, and then I will certainly mention that. Zigong
Okay.
asks, what are the deliverables of structural interpretation?
For the structural interpretation, what we would expect is a mapping of the different fault systems. There may be faults of only one age. There may be multiple fault episodes. We would want to know how those faults intersect the key horizons. We'd want to know the timing of fault movement. And then we would want to know the location of structural traps and what might be the controlling factor in terms of how far down dip might we expect oil or gas to be trapped. So are there any leak points or spill points that can determine? And sometimes those are subseismic faults, and so they can be difficult to determine before drilling.
Okay. Zhao Zhang also wrote in and said, what is the current state of FWI, which I'm assuming means full waveform inversion? It's computationally heavy and has that limited its usage.
Yeah, I know that a lot of research work is being done on that. I think the technology exists, but it is pretty expensive. And I expect in the next maybe 5 years or so, people will come up with faster, cheaper ways to do full waveform inversion, and that will become more and more a tool that people not only want but will demand. I know with the unconventional or resource plays where they're drilling very low porosity rocks and trying to get oil and gas, that inversion is being used a lot in order to geosteer the wells to try to maximize their production.
Okay. Well, great. Thank you, Fred. And as Fred mentioned, we are planning to record this webinar as it's been recorded today, but then for people who may not have been able to attend, what we'd like to start doing is some tweet chats with previously recorded webinars so that Fred will be available to answer questions. We're scoping out potential dates, probably likely in late June. But we also, I forgot to mention, there's a whole course load of Fred's lectures and exercises and material that's available through our IRIS in class, which is our teaching repository of information. It also houses all of the educational resources that IRIS develops. So you can just look on that on our main website /in-class and be able to find that information. And currently we have 17 of Fred's lectures archived there, and working on the second semester of materials. So we kind of hope to be able to help you in the classroom setting in any way that we possibly can. So, so with that, thank you so much, all of you, for your great questions. Thank you, Fred, for giving this webinar today. And with that, this concludes our webinar, and thank you so much for attending and participating. All right.
And my thanks to everyone as well, including to Danielle.
Thanks. Thanks. Bye, everybody.